I'm Augustus, and I'm going to talk about work that I did at Google Brain with Jonathon, Shlens, and Olah. Oh shoot, why is it doing this? There you go. Okay, so this is like sort of the results of the work. These are samples, and I think for like a month, maybe these were like the nicest ImageNet samples, and now there are much better ones. Okay, so basically we did two tricks to get it to work. So I'm going to describe two tricks and then like 3 experiments. The first trick is and this is pretty similar to a lot of other tricks that have been done, right? You factor out the labels from the noise. You feed both of them through the generator. Now you ask the discriminator, tell me, is the thing I'm seeing fake? And also, what is its label, right? And then you train the generator to sort of enforce that the discriminator gets the label right and it gets the source wrong. And the discriminator, of course, it wants to get everything right. That's the one trick. The second trick is that on ImageNet, it's hard to get GANs to work, I think because there are so many classes. I think this is sort of batch norm's fault, but I don't want to like say anything really confident about that. But what we did was we just split up the generators into a bunch of groups and delegate you're going to deal with classes 1 through 10, and you're going to deal with classes 10 through 20, and that seems to help a lot. Cool. So those are the tricks, and these are the experiments. When you're generating a high-resolution image, like to the extent that you can say 128 by 128 is high resolution, you'd like to know that it's not just a naive resizing of a low-resolution image. And so one way you can do, so like if it were a naive resizing of a low-resolution image, if you downsampled it and then took some sort of measure of image quality, you shouldn't see the measure of image quality really degrade much as the downsampling happens. But we did a bunch of experiments along these lines, and it seems like actually generating high-resolution images makes the samples like more object-like. The details of the experiments are sort of hard to describe in a short amount of time, so come to the poster, I guess, if you want to hear about them. Let's see. Oh yeah, okay. So we came up with an ad hoc method for measuring the diversity of the samples. So there's this, I don't know if it's probably like old school is the wrong word. There's this multi-scaled structural similarity index, right? It's a measure of how similar two images are to each other. And it has a bunch of parameters, and you tweak them such that they match up with human perceptual judgments of image similarity, right? So one thing you could do to measure diversity of the samples from a class-conditional model is you can look at all the samples from a given class and then take the average pairwise MSS sim between them. And that's what we did. And we did a bunch of variations on that experiment, but basically it turns out that, as you would expect, the generated samples are a lot less diverse than the training data, but they're still like reasonably diverse. So this red dotted line, if you can see it, that's the diversity of the least diverse class from the training data. And in the experiment we did, like 87% or something of the sampled classes had diversity more than that. They were more diverse than that class. So it's like doing something kind of reasonable. Yes, and you might be concerned that the GAN achieves like good objectness at the expense of variability. And so we plotted variability next to our measure of objectness, and it seems like that isn't really true, which is encouraging. And that's what we did. If you want to know more, come by the poster.